All right. And we're live for the 0 people that are online right now. Fantastic. Now, in regards to the rest of this week, yes, I've already given you that quizzes. I am going to be assigning something probably today or tomorrow. It may not be a quizzes, but it'll be something online for you to be able to do. I want to assign you something out of the textbook. There are still a few lingering people who have not logged on to the textbook yet. If you haven't, you need to get on top of that. But I will be assigning you something out of that textbook. It's going to be great and fun, whatever. And then on Friday, if we have the opportunity to do so, because I would be very available and very willing to do this, on Friday, I may be able to review some of those practice problems with you. And that would be wonderful, because that's what Friday is supposed to be about. Practicing and catching up and blah, 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 blah. Yay, oh, happy day. I see there's one person in the chat, but I don't know if they're going to say hello. Hello, hello, hello. Is this person gone? Nobody knows? You're like, I don't even know who's sitting there. I don't care. Okay. We'll see what happens. Anyway, ladies and gentlemen, I have a short video for you to watch that I'm going to throw over here. Now, before I play the video, full disclosure, number one, I did not make this video. Number two, this video is a little corny in terms of the animation and stuff like that, but it does have important things that I need you to focus on, important things that are going to inform what we are going to be doing today. There is also a part in the video that I am going to skip over, not because it's inappropriate or anything like that, but just because I didn't find it relevant to what we are doing. So I'm going to skip by that part when I get there. Oh, it's Cryptify. Who's It's Cryptify? Oh, there it is. It's Tristan. Hey, what's up? Yeah. Sorry, it's so weird when you guys go on like YouTube, you might automatically be signed on to like your personal account. I do that a lot too, sometimes by accident, and then you gotta switch over. Whatever. Anyone subscribed to my personal YouTube yet? No? I just broke 2 world records for video games. Go look it up. Not now. Yeah, legitimately. I broke 2 world records. Hold on. For a video game, for the original NES. Here, okay, I won't show you the video, but I will show you the proof. Chapow. Look at those 2 gold trophies. Those are world records. Be jealous. Anyway, I want you to focus on what this guy is saying in this video. Again, forgive the corniness.
Hello, I'm Professor Von Schmohawk, and welcome to YU. So far, we have introduced quadratic functions and have seen that the graph of a quadratic function in a single variable is a parabola. If we set a quadratic function equal to 0, we produce a quadratic equation. Although quadratic functions and quadratic equations look similar, there are some important differences. For example, let's take the quadratic function x squared minus 4. Like all quadratic functions, the graph of this function is a parabola. Now, if we set this function equal to 0, we produce a quadratic equation. This equation has 2 solutions, x equals 2 and x equals -2. So although the graph of the function x squared minus 4 is a parabola, the solutions to the quadratic equation are the 2 points where the parabola intersects the x-axis, also known as its x-intercepts. These points are called the zeros of the function. In general, the zeros of a function are the input values that cause the function's output to have a value of 0. So for a function of x, the values of x which cause the function to produce a value of 0 are the zeros of the function. These zeros are sometimes called the roots of the function. Finding the zeros of a linear function is easy, since unless the function's graph is a horizontal line, it will always have a single x-intercept and thus a single zero. To find the zero of a linear function, we determine its x-intercept by setting the function equal to 0 and then solving the equation for x. On the other hand, a quadratic function of a real variable may have two x-intercepts, one x-intercept, or no x-intercepts. But solving a quadratic equation can be much more complicated than solving a linear equation.
Oh, hold on.
The problem of finding the solution to simple quadratic equations was encountered at least 4,000 years
This is the part that I'm going to skip over. Hold on.
ago. It is that the average model socks square link root in action saw AI talk about is of free-fall quadratic equations. For instance, the trajectory of a free-falling object can be described by a quadratic equation. As an example, if a cannonball is fired from a cannon 12 meters above the ground.
Boom. Now, I'm going to pause it here. I'm going to play the rest of the video in a moment. But this is the part that I wanted to jump to. The entire purpose of... Wait, what is that? Sub with both. Okay. The entire purpose of solving these quadratic equations is to be able to find a very particular, important, earth-shattering point. And this is that earth-shattering point right there. The point at which it hits the ground or it hits whatever target you are aiming at. This is going to be one of the main things that we're going to be focused on with quadratic equations and solving them. So I'm going to let this guy finish, and then I'm going to get into what I need to get into.
And the cannonball has an initial vertical velocity of 80 meters per second. Then, according to the laws of Newtonian mechanics, the height of the cannonball above the ground would be given by the function -5t squared plus 80t plus 12, where the constants in this quadratic expression are determined by the physical parameters of the example, and t is the time elapsed after the cannon is fired. If we wish to find the time it takes for the cannonball to hit the ground, we set this expression for the vertical height equal to 0. And solve the resulting quadratic equation for t. Solving this equation requires a mathematical technique more powerful than anything that the Babylonians or Egyptians had in their mathematical bag of tricks. In the next several lectures,
we're not watching the next several lectures. What we're doing instead is this. Ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. Now, while you're doing that, let me talk very briefly about the Babylonians. The Babylonians had a lot of advanced mathematical techniques, but there came certain quadratic equations that they were not able to solve because they did not have all the tools that were necessary. Today, we are mainly focusing on the tools of factoring. We are going to be able to factor quadratic equations in order to solve them. Eventually, we are going to get to a point where we will be unable to solve quadratic equations by just pure factoring, because there are going to be some quadratic equations that are not factorable. So I ask you the following question. If you cannot factor a quadratic equation, is there some kind of formula that you've had nightmares about that they taught you a few years ago? Anyone remember that formula off the top of their head? Not to give you some PTSD. Anyone remember that whole negative b plus or minus square root b squared minus 4ac all over 2a? It will eventually come back into play. The purpose of today's lesson is not to dive into that formula, the quadratic formula. We only rely on the quadratic formula if we have no other option. Today, we do have those options. The quizzes that you guys did for me involved everything with factoring, quadratics. Now we are going to be taking it a step farther. So, in your notes, this is exactly what I'm going to title this thing. Come here, chair. I got a chair. We're going to entitle this thing Solving Quadratics by Factoring. Today is the 23rd. Excellent. Oh, goodness. Sorry. For those of you in the chat, I am loading the window on my phone so I can see it from where I am in the room. So I should be able to see the chat in all of its glory. There you guys are. But let's start with something like this. Let's say that I said to solve the following quadratic. Now, this has been the goal since I don't know when. This has been the goal of math students since they first introduced variables to you. The idea that you were given an equation and you are told to solve for x. What does it mean to solve for x? What do you do to the x in order to solve it? Okay. If you could manipulate it using algebraic means, ultimately at the end, let's just say the answer is like 2. Let's say the answer is supposed to be 2. After I do all of that junk, what would show up at the bottom if the answer was 2? X equals 2. If it were 2. I have no idea what the answer is off the top of my head. If the answer is 2, then you'd be like x equals 2 at the bottom. You've heard the phrase isolate x. Get x by itself. That is the goal of a lot of these mathematical problems, to be able to determine what value of x will give me the answer to this particular problem. Now, in the video that I just showed you guys, they talked a lot about when it would hit the ground, when it would cross the x-axis. Desmos is an amazing resource. Let's see. There we go. What you see visually on the board right now is the equation that we're dealing with. This is x squared plus x minus 6. And the 2 points in question, by the way, this is total coincidence, absolute total coincidence. What x value is that? Is it 2? That was total coincidence. I said 2 just because I wanted to, but it just ended up being 2 is one of the answers. Boom, you also have a second answer. The general idea of solving quadratics is being able to find those 2 points. Being able to find when the quadratic crosses that particular x-axis. I'm going to write a lot of this stuff down. You're going to see it, and I'm going to hopefully get you to understand why and how this stuff all works together. The general idea of that cannonball example is, and this happened a lot in, let's say, like revolutionary times, where you had like a guy running a cannonball, and then boom, the cannonball is shot and fired, and it's going in this direction. And then there are some troops that are running up the hill. Oh no, blah, 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 blah. And they're running up the hill. And the idea is that you want that cannonball to land right in the middle. So you have to time it out or do the math. If you do the math very quickly, you could determine precisely where that cannonball is going to land and hit the ground as if the ground were the x-axis. That is why during the Civil War, during the Revolutionary War, the most important person on the battlefield was the mathematician, because the mathematician could do easy calculations like that very quickly in their head in order to determine the maximum way to kill people. Did you know that it is during war times, that mathematical advancements are made. It's pretty crazy. There's a movie a few years ago with Benedict Cumberbatch. I think it was called The Imitation Game. Anyone ever hear of it? You guys are lame. Yeah. It was about the Enigma code machine that a mathematician during World War II was able to crack. It's pretty awesome. Anyway, let's start this. I said to solve this by factoring. Now, we have factored this a number of times. We've factored this multiple times last week. I want to factor it again. So I want to remind you of the Tucker method, and you got to help me out with this. What's the first step of the Tucker method? GCF, which in this case, it's a 1, and a -6. I can't do anything. Move on to the next step. What is the next step? Almost. There's one extra little step that you got to remember to do just in case. Step 2 of the Tucker method. Now, were you referring to like a different method of factoring? Okay, I was just double checking. Step 1 was GCF. Step 2, A times C. Now again, I'm not forcing anyone to use the Tucker method. I am not forcing anyone to use the Tucker method. That is not the purpose of this. If you have a different way of factoring that works, stick with that method. I'm just simply showing you an alternate way. A times C would get you -6. Now I got to find those two magic numbers. Two magic numbers that multiply to -6 and add up to the B value. 3 and -2. 3 and -2 definitely work here. They multiply to get you -6, and they add up to the B value, which is +1. You could do a T-chart if you wanted to, although a T-chart is not really necessary here. Magic numbers go on the bottom. It's a 1x squared, so it's a 1x and a 1x, which means this ends up being x plus 3 times x minus 2 equals 0. Couple things. Number 1, have you ever looked at an equals 0 by turning your head to the left and seeing it as a weird face? The question was, have you ever looked at an equals 0 and turn your head to the left to see the weird face? No. Now you will never unsee it. You will never unsee it. Just saying. Anyway, second, this is not my answer. This is not my answer. These two terms are my factors, not the answer. As we said at the beginning, solving an equation means to get the variable by itself. Ultimately, at the bottom, at the end, when we get to our answer will be x equals something. This is not my answer, but these are the factors. The whole purpose of the Tucker method was to factor. The purpose of the Tucker method was to factor. That completes the Tucker method. That legitimately, we're done with the Tucker method. But now we have to move on to something else, which is the purpose of today. A couple of pieces of information for you all. To solve a quadratic means to find the x-intercepts, as we talked about before when I was on Desmos. On Desmos, we talked about the x-intercepts, and I'm going to go into more detail as to what it means to be an x-intercept in a little bit. But you could call them an x-intercept all you want. On the video, they talked about the other names. There are other names besides x-intercepts that we're looking for. Yes, to solve a quadratic, you could find the x-intercepts. You could also say roots. You could also say solutions. You could also say zeros. All four of these terms, all four, mean the same thing. They are interchangeable. You might be faced. Yeah. I apologize for the light issue. They're in the chat. They're telling me about the light bulb issue. It's not really so much of a quote unquote fix. It's not like I can like twist a screw and get that light issue taken care of. It's a matter of the administration and the IT department getting together and allowing me to use a different form of live streaming. And if and when they eventually do that, I can't do anything about it until then. It's okay. Yeah, I know it does. Anyway, I'm talking to him. I'm not talking to you. Anyway, they all mean the same thing. They may ask, hey, find the x-intercepts of this quadratic, or identify the roots of this quadratic, or find the solutions to this quadratic, or hey, find the zeros of this quadratic. They all mean the same thing. They all mean the same thing. That's what they want. So we have to go down to the idea of, well, if that's what we're finding, then how do we do it? Let me give you another statement. To solve a quadratic means to let y equal 0. Now, this is important. This is very important. This statement right here, this is probably one of the more important statements that you're going to hear today. Letting y equal 0. I'm drawing a picture for funsies. Which one is the x-axis? You can show me with your hands. Which one is the x-axis? Thank you. This is the x-axis, which means if I'm right here, this point would be considered an x-intercept. If I'm on the x-axis, I am an x-intercept. Remember, to solve it means to find the x-intercept. And I don't know what this number is. Let's just say this number is like, I don't know, 3. If the x-intercept is 3, it's the ordered pair 3, comma, what? 0. Now that's the key. You want to find an x-intercept? You let y equal 0. You want to solve a quadratic? You let y equal 0. And the moment that you let y equal 0, you are on your way to solving this quadratic. This gives me the justification. This gives me the justification to do the following. I started with y equals x squared plus x minus 6. Because of what I just wrote, I can say x or 0 equals x squared plus x minus 6. And because of what we did with the Tucker method, I can say 0 equals x plus 3, x minus 2. Let me recap exactly what the heck just happened, because I want to walk you through what just happened. First of all, last week we talked about factoring. Factoring quadratics, ripping them apart to their prime factors. Oh, happy day. Then, talked about solving a quadratic. To solve a quadratic means that you are going to find the x-intercepts, the zeros, the solutions, the roots. You want to find those? There might be 1, there might be 2, there might be none. But if you want to find them, you have to let y equal 0. The moment that you let y equal 0, we are on our way to solving this problem. Boom. This quadratic can be factored. Boom. And now we have justification behind what I'm about to do next. It's going to be a magical step. Magical for me, not for you. I don't know when you first learned this. I don't know if it was like 3rd grade or 4th grade. When do you first learn multiplication? Just multiplication. Is that like 4th grade, 3rd grade, 10th grade, 2nd grade, kindergarten? But still, what happens when you multiply two things together and the result is 0? What happens when you multiply two things together and the result is 0? What do you know about those things? Do you know which one? Could they both be? They both could be. Doesn't matter, but you're guaranteed that one of them is 0. At least one of them is 0. When you multiply two things together and the result is 0, one of them has to be 0. What's this operation right here? And what does it equal? That's the key. You have two things being multiplied together and the result is 0. You are guaranteed then that one of those two things, could be both, but one of those things is definitely equal to 0. Let me show you where this is going to go. I got to give you a side note. Side note. Literally, I'm going to call it a side note. If A times B is equal to 0. You remember if-then statements from last year? That just sent a chill up all of your spines by reminding you of geometry? Just saying, I don't know. If A times B is equal to 0, then either A equals 0 or B equals 0. Could be both. Could be both. Which means, for us, either x plus 3 is equal to 0 or x minus 2 is equal to 0. Let me bring this up a little bit. There we go. We don't know which one. We don't know which one, but we have to assume both. Hey, we could solve that. What do you do? Just very briefly, what do I do to get x by itself? Yeah, subtract 3. And then over here? Add the 2. Yeah, oh, I got that. I don't even need to do anything, really. Subtract the 3. Add the 2. Nailed it. Oh, happy day. Oh, happy day. Nailed it. Oh, these are my solutions. They are my roots. They are my x-intercepts. They are my zeros. When you are faced with a problem, you may see them being called any of those things. And I want you to be aware of the fact that any of those things are referencing the exact same thing. They all mean the same thing. It is nuts. I was doing, was Monday back to school night? Yeah, Monday was back to school night. And I was doing back to school night, and I was sitting at my desk, and I was holding this, and one of the parents, like, legitimately asked me, like, what is that? Is that, like, some kind of, like, weird, like, that thing that you have the microphone in? Is that some kind of weird device that helps you, like, broadcast? I'm like, no, it's literally just a cardboard tube. It's fantastic. You know why I have the cardboard tube? So it doesn't roll away when I set it down. Like, look, right. I need to write. I can't just keep holding the microphone, you know? Like, can you imagine if I was literally just like this the whole time? That would be weird. I like this. Anyway, back to me. Let's see what we got now. Now, just to recap something real quick, because I'm going to write it on the board. Where'd you go? There you go. There you go. I'm just going to write this, but I'm going to erase this just as fast. Just please keep that in mind. x squared plus x minus 6 equals 0. What were one of the two solutions? -3. Watch this. -3. -3. -3 squared. Yeah, we did it. Good job. 9 plus -3. 6 minus 6. Yeah. What's the other answer? 2. The other answer was 2. I'll do this one for you. 2 squared is 4. 4 plus 2 is 6. 6 minus 6 is 0. It works. Could you logically, could you eventually, guess and check that answer? Yeah, of course you could. Of course you could. But they're not always going to be that simple. They are not always going to be that simple. Man, I wonder if he said they're not always going to be that simple because he was foreshadowing the next problem. Garbage can. It got in my way, so I kicked it. Example. Solve 2x squared plus 9x plus 4 equals 0. Now, this is a problem where it's not as simple. This is not as simple. Let's take a look at the graph. Let's just take a look at the graph. I don't know. Maybe the graph will have something. Let's go to Desmos. 2, 9, plus 4. Cool, we got a quadratic. There's the brand new quadratic. If you haven't used Desmos, you're missing out. Desmos is fantastic. Just saying. But yeah, there's the quadratic. It clearly has 2 x-intercepts. It has 2 x-intercepts. Happy day. You could even visually identify what they are. Like this one looks like a -4, right? What's this one look like? Yeah, it's not a whole number. It looks like negative a decimal. You could guess it. I don't know. How do we know for sure? Let's go through the process. Let's go through the process. Solving this by factoring. If I were to go about solving this by factoring, let's start with greatest common factor. Greatest common factor. Oh, man. Hey, look, they have a 2 in common. But this one doesn't. They have to all 3 have the same greatest common factor. So I move on to A times C. 2 times 4 is 8. I need 2 magic numbers. Yep. 8 and 1. People sometimes forget the 1. Some people sometimes forget that they can do a 1 with this thing, you know? But yeah, 8 and 1 totally work. Absolutely. So I go to my T-chart. 8 and 1. Hey, what do I put on the top? Before I did a 1x and a 1x. What do I do here? What must I do here? Ooh. Before I just did a 1x, a 1x. I got to do a 2x, 2x here. I'm going to 2x and 2x this thing because of the 2x squared. Now, eventually, it's not going to stay 2x and 2x. Something might get reduced. Something might get reduced. Interesting. Sorry, I'm getting emails by the wazoo. So I got to reduce this crap. 2 over 8 reduces to a 1 over 4. 2 over 1, I'm going to keep it a 2 over 1. This becomes a 1x plus 4, and a 2x plus 1 equals 0. Phenomenal. When it comes to solving quadratics, you are either going to solve them by factoring, or you are going to solve them by the quadratic formula. If factoring works, stick with factoring. If you have no choice, then use the quad formula. But I haven't taught you the quad formula. Were you guys taught the quad formula in Algebra 1? Several people are nodding yes. I'm afraid to ask the next question. Were you taught it in such a way where you'd remember how to do it? Everyone nods no. Anyway, back to this. Factoring. I was able to take this quadratic. I was able to use the Tucker method. I was able to rip that thing apart into two factors. Now that these two factors are being multiplied together equal to 0, I can use that side note otherwise known as the zero product property, and I can take the x plus 4 and set it equal to 0, and the 2x plus 1 and set it equal to 0. Now I can solve this like it was a pre-algebra problem, where I get an answer of a -4. Oh, happy day. We knew it was -4. What was the other answer? How do I solve this? Cricket, cricket. I hear crickets. How do I solve this? This pre-algebra type problem where I need to get x by itself. What do I do first? Subtract 1, then divide by 2. Oh, -1/2. I got that. -0.5. There's your negative decimal answer. I'm going to show you something wonderful on Desmos. Hold on. Check out Desmos. Watch what happens when I bring the mouse over here. I can click and actually secure fixed points on that graph. Desmos is fantastic. I understand that a lot of you use the TI-84 calculator for various things. That's fantastic, wonderful. But if you have to do anything with graphing, Desmos might be your better shot. With Desmos, you could do a lot of different things. It's really wonderful. Hold on, let me see if I can do something here. Can I add a slide? I want to add a slide. I don't know if it'll let me. It won't let me. Maybe I'll do it here. Hold on. A. Yep, add A. Yes. Check this junk out. Look at this junk. Look at this junk. Look at this. Yeah, I can do this where it's like slide. Sorry, I'm having too much fun. Go away, Desmos. Come back to this screen. Why do they let me do this job? Okay. What type of math problem could we do that would scare most people? What type of math problem gives people the most anxiety? What type of math problem haunts your dreams and sends chills up your spine? Do you know? I know. Agree or disagree? Word problems. Immediately. I love word problems. Word problems are my bread and butter. They're wonderful. It's so good. Now, with word problems, ladies and gentlemen, that is going to be one of the bases for the project that I am going to assign you in the next couple weeks. I am going to be assigning you a project, and it is going to be based on a lot of word problems. In fact, I told you at the beginning of class that I was going to assign you something out of the textbook. I'm assigning you some word problems, and it's going to be wonderful. Everyone's all avoiding eye contact right now. It's great. It's so great. I wake up in the morning and I think to myself, how in the world can I get through my day? I know. I'm going to torture some high school students. What other job would allow me to have this much fun? Okay. You're building a fence. You're building a rectangular fencing area. Here's the example. I'm building a rectangular fencing area, and in order to fit it into the area that I need, the length needs to be 6 feet more than the width. The length has to be 6 feet more than the width. You could use W's and L's and all that fun stuff. I'm going to use X here. There we go. I just nailed that. The length has to be 6 feet more than the width. Okay. The total area is 16 feet squared. So then the question becomes, what is the width x? That's the question. What is the width of x? Now, I'm going to be very, 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 very honest with you. With a problem as straightforward as this, I guarantee that you would be able to solve this in your head. I bet you can. I bet you that you could just look at this problem, think about it, change some things around, and literally figure out what the answer is supposed to be just by thinking about it. Good for you. Fantastic. Awesome. The problems are not always going to be that straightforward. They're not. Anyone got this answer? The value of x? Yeah? Not for this one. If it were 5, think of it this way. If it were 5, it'd be 5 and then 5 plus 6, so it'd be 5 times 11. What do you got? What should the number be in order to hit 16 square feet? Remember, to find the area of a rectangle, you got to do what? Length times width? What number for x makes this work? It's got to be 2. 2 is the only one that works. 2 times 8. 2 times 8. You plug in a 2 for both x's. Yay, we did it. Oh, happy day. But I need to see the work. I need to see the algebra. I want to see the algebraic manipulation of this problem in order to get the answer that we are looking for. Because that is what I'm going to be expecting on this assignment that I'm going to give you. This is what I'm going to be expecting on that project that I'm going to give you. Oh, happy day. Here we go. The area of a rectangle is length times width. So, if I multiply these two terms together, that should give me the area of this rectangle. But I know what the area is. The area is 16. So, I'm going to set it equal to 16. This is the setup to the problem. You take the word problem and you manipulate it into an algebraic equation that will help you. I'm going to have to do something special here. I'm going to have to do this. You guys remember what that's called, right? What am I doing there? Yeah, you're distributing. Because I got to simplify this crap out. If I distribute that x, I'm going to get an x squared plus 6x equals 16. Okay, there's my quadratic. I see the quadratic. I see the quadratic. Oh, weird. Sorry, I'm getting more emails like every day. So, I got to solve this crap. I got to solve this garbage. Wait a minute. Something looks weird. Something looks weird. Did we make a mistake? Something feels off. Something feels really off. The first problem that we did today was this. The second problem we did today was this. And now this is the third problem we're doing today. What feels off about this? Kinda. Like, but C could be 0, right? It's not equal to 0. Ladies and gentlemen, in the video that I showed you this morning, they made a big deal about setting the equation equal to 0. I made a big deal about it setting equal to 0. I said, you got to let that y equal 0. I said that you were finding the x-intercepts. You were finding the zeros of the function. In order to do this, you said, like, clearly you're looking at this and you're like, oh crap, it's equal to 0. It's equal to 0. It's not equal to 0. What do I have to do in order to get it equal to 0? Well, you just move stuff around. If you literally just move stuff around, You can manipulate the way this problem looks. You can manipulate it by simply subtracting the 16. You end up with x squared plus 6x minus 16 equals 0. That's one of the main purposes of this problem. Get one side equal to 0. If you get one side equal to 0, then you are golden. Move on to the next step. But you need to get one side equal to 0. Now I'm gonna leapfrog a little bit. Let's assume I did the Tucker method. If I did the Tucker method here, I end up with these two terms. Then, when I use that side note, that zero product property, when I use that zero product property, I end up with x plus 8 equals 0 and x minus 2 equals 0, giving me these two answers. Oh, happy day. Oh, yeah, that was the answer he gave me before. He gave me 2. I didn't circle my answer yet, though. There's a reason why I didn't circle my answer yet. There's a reason why I have not circled it. Ooh, I wonder why. Ladies and gentlemen, this be a word problem. And if you have a word problem deserves units. You said the answer was 2 before. Yes, I agree. The answer is 2. 2 what? 2 what? What's the context of this problem? We're talking about the area of a rectangle, or the length and width of a rectangle. It's 2 what? Say again? Somebody's whispering it. Feet. Yeah, we did it. Good job, crew. It's feet. I got to put the word feet on there. So then I ask you the most important question. Question? Yes, you just got to fill out something for me. Here, fill this out in pen. And I'll be with you in a minute. Ladies and gentlemen, I'm going to write this down real quick. Feet, because of the context of the problem. So I ask you the most important question. What do I do with the negative 8? What do I do with the negative 8? I got 2 answers. There are typically 2 answers to a quadratic. Negative 8 cannot be an answer. If I plugged in negative 8 would work. Algebraically, it would work. Algebraically, it would work perfectly. If I plugged in a negative 8, I would get negative 8 times negative 2, which works. But you can't have negative 8 feet. You cannot have negative 8 feet. You just cross that sucker out. This only happens in word problems. Sometimes you will get an answer that does not make sense in the context of the problem. You always have to look at the context of the problem. Positive, negative has nothing to do with it. Negative 8 feet? I don't think so. Sometimes you might get a positive answer that makes no sense. It depends. It depends on the context of the problem. Here's what I want to do. I have 2 problems for you. I have 2 problems that I want you to try. I'm going to give you a little bit of time to knock them out to get me my final answers. Let's write them down, and then I'm going to talk a little bit about them. Oop, come on, chair. This chair needs to cooperate. I got 2 problems. Split, solve, x squared equals 2x plus 99. Solve 2x squared minus 8x minus 90 equals 0. A couple things about these problems before you begin. First and foremost, this problem is not equal to 0. You have to make it equal to 0. You are going to have to move the terms over in order to get one side equal to 0. It is in your best interest to keep that x squared a positive number. It is in your best interest to keep that x squared positive. So move everything over to the left. In the second problem, yes, there is a greatest common factor. You need to take that greatest common factor out. That's what I want you to do. I'm going to give you the next less than 5 minutes or so. 5 minutes or less. Knock out these two problems. Get me my solutions. Let's go. Not that I'm advertising, but I just realized I had a Wawa sub for lunch. And my spirits just lifted. Just saying. You get a Wawa sub for lunch, but you got it. Oh, sorry, it's over here for some reason. It's really just be by the door. So I don't know what what the last part you were here for, but I assigned these two to try for practice. I specifically said the problem on the left, you had to get one side equal to 0. The problem on the right, you have to take out a greatest common factor. Yeah. Here, fill this out. In a pen. You ever have ear fatigue with these things? With the masks? Ear fatigue? No? I'm getting a lot of ear fatigue today. Oh, I'll finish it up. Oh, gosh, I just dropped my glasses again. What is wrong with these things today? It's C205, but I'll get it. A little better. Oh, you got it there. Yep. you guys. I'm so excited. You guys have these stoves nowadays where you turn the knob and it goes like click, 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 and then the flame goes on. Back in the day, we had these things called pilot lights. You know what they were? On these old stoves, my mom had this old stove. Actually, let me get on the microphone. This is a good speech. On these old stoves that my mom had back in the day, you had like this little metal circle, and if you looked into it, this hole, you would actually see a little blue flame, and that flame would be there all the time. So when you went to turn on the stove, it would go, it wouldn't even click. It would just automatically be on all the time. So when I was like 4 or 5 years old, I climbed up on the counter and I looked down and I saw this pilot light. And I thought to myself, I've never seen blue fire before. I wonder what it feels like. So I took my thumb and I put it over the flame, like right on top of the stove. What do you think happened? Yeah, burnt my thumb. Ouch. Cried, 2nd degree burns, the whole deal. Here's the thing. High school students in math class are afraid to get burned. I'm not advocating that you go put your hands in fire. That's not what I'm advocating. High school students are afraid to get burned in math class. Instead of using the phrase getting burned, let's say being wrong. High school students are afraid to be wrong in math class. The idea is that, well, consciously or subconsciously, Mr. Markey, if I don't try the problem, I can't get it wrong. You're afraid to be wrong. I ask a question or I say try a problem, people are like, I don't know how to do this. And since I don't know how to do this, I'm not going to try. No, that's no excuse. You're afraid to be burned. High school students are afraid to be burned, and because they're afraid to be burned, they're afraid to be wrong, they're afraid to try the problem, get it wrong. Because of that mentality, we don't learn. The best way to learn something is to try, to mess up, and to be corrected. You better believe, after I burnt my thumb and after my mom yelled at me, do you think I touched that stove again? Well, not the flame. The stove itself, yeah, probably, but not that flame. Because I learned something. I was willing to put myself out there. I was willing to make a mistake because I had no idea what I was doing, but I learned something. See, the thing is, like a high school student, a lot of the time thinks, if I just sit here and watch, I'll get it. No, you won't. Not all of it. Some of it maybe, but not all of it. You have to be willing to get your hands dirty. You have to be willing to make a mistake. You have to be willing to let yourself get burned on a problem, figuratively speaking. Again, do not go walk into fire. That would be ridiculous. Oh, watch feet, watch feet, watch feet, watch feet, watch feet. Cool. The best type of math student. Some people think, like Mr. Markey, the best type of math student is just someone who like gets it right all the time. No. The best type of math student is one who tries, gets it wrong, and is willing to work towards getting the correct answer. That's the best type of math student. Let's do these two problems. I'm looking at this first one. X squared equals 2x plus 99. I'm going to subtract the 2x and the 99. It is in your best interest to have that x squared be positive. You could do that A times C action going on here. Holy crap, I got negative 99? Ugh. Wait a minute. What are two easy numbers that multiply to 99? Negative 11 and 9. I know, when I see like a 99 like that, I'm thinking like, oh crap, it could be like what, 1 and 99, it could be like 3 and 33, it could be, that I don't think that's divisible by 6. No, it's not divisible by 6 decimally, definitely divisible by 9. A lot of options, but yeah, those two numbers work. The t-chart won't do anything. So I end up with x minus 11 and x plus 9 equals 0. A reminder, your magic numbers are not the answer. Your magic numbers are not the answer. Your magic numbers are simply a means to getting the factors. Once you have the factors equal to 0, then you can go about the process of beginning to solve them, where you get two answers, 11 and -9. It works out amazingly. It works out so nicely. Let me show you something really cool, actually. Check this out. Let me show you something really cool. So the answers were +11, +11, and -9. Check this junk out. Oh, yeah, let me go -12 to +12. There we go. And let me go 0 to 150. Boom. There's the parabola. There's the straight line. Now, what's really nice about this is, again, if I go back to the original problem right here, you have an x squared equal to a linear equation. And what's really nice about this, what were my two answers to this problem, by the way? The two numbers, answers, solutions, x-intercepts, roots. Check this out. 11, +11. Boom. Look where +11's hanging out. You know what that's called? A point of intersection. A point of intersection. What was the other answer? You said 11 and what? -9. You can pretty much guess where this is going to be. It's exactly where we thought it was. See, the thing is, when we change it up to where I say -2x and -99, once we change that up, now all of a sudden, I get that -9. There it is, x-intercept, and +11 x-intercept. It just shifts everything down. Oh, it's so wonderful. Let's look at the second problem. This problem had an Egyptian king in common. It had an Egyptian king in common. It had a 2 in common. Hilarious knee slapper. You take out that 2, it is a factor to the problem. Let's pretend I went through the Tucker method. If I went through the Tucker method, here are the two factors that end up from the Tucker method. How many factors do I have here? How many total factors do I have in this problem? Ooh, you're saying 2. I actually have 3. What do you believe the factors are? They are definitely factors, but so is the 2. Because remember, the 2 was your GCF, your greatest common factor. It counts as a factor. So I take all 3 of those and I set them equal to 0. Wait a minute. That first one makes no sense. That first one makes no sense. I agree. That first one makes no sense. Cross it out. 2 can't equal 0. 2 can't equal 0. But you do get 2 answers. +9, -5. Ladies and gentlemen, I'm going to be assigning this on Google Classroom for you. But I am going to be assigning you something out of the textbook. I am going to be assigning you something out of the textbook in regards to word problems. Good question. Those were the magic numbers from the Tucker method. If I did the Tucker method with this quadratic, it'd be 1 times -45, so I'd get -45. -9 times 5, -9 plus 5. That's where they came from. Mm-hmm. Thank you for asking, though. If you do have clarification questions, ask them. Absolutely, yes. On Friday, I am hoping if you have any questions in regards to the word problems from your homework, again, it's not really homework, it's like classwork participation work, but whatever. If you have any questions in regards to that, I will gladly go over that with you on Friday during a live stream, and we'll see where this kind of takes us. Anyway, I'm going to sign off in the thing, and then we'll go from there. Question?